Hi everyone, this is Professor M. Science, and today we're going to derive the angular momentum eigenvalues in another one of our videos on rigorous quantum mechanics. We know that physical quantities in quantum mechanics are represented by operators, and that the most important equation associated with these operators is the eigenvalue equation. For example, it can tell us about the different outcomes of a measurement. Today, we will explore the eigenvalue equation of angular momentum operators. We will learn that angular momentum cannot take just any value. It is actually quantized. This video will cover the mathematical derivation of angular momentum eigenvalues. And although it is a little bit heavy on the mathematical side, it has some really neat, very visual steps that will give you a very clear understanding of what is going on. It is also very similar to the strategy used to figure out the eigenvalues of the quantum harmonic oscillator. So what you will learn today will be useful beyond angular momentum. You can also find a companion video linked in the description where you will find a discussion of the more interesting features and conventions associated with the eigenvalues of angular momentum. So let's go! Let's start with a quick refresher of angular momentum in quantum mechanics. We consider a vector operator J that is made of three operators J1, J2, and J3. The operator J is an angular momentum operator if the three components obey these commutation relations. You will remember from the video on angular momentum that epsilon ijk is the Levi-Civita symbol, and that we're using Einstein notation so that an expression like this implies a sum over repeated indices, in this case over the k indices. This is a definition of a general angular momentum in quantum mechanics, which includes the orbital angular momentum that we're familiar with from classical mechanics, as well as the spin angular momentum that doesn't have a classical analogue. Today we will work with the general angular momentum, so the results will in principle be relevant for both orbital and spin variants. Now, another important thing to remember is that as the different angular momentum components don't commute, they don't form a set of compatible observables. What we found in the video that introduces angular momentum was that we can define a new operator j squared equal to j1 squared plus j2 squared plus j3 squared. And that this operator j squared does commute with each individual component. This means that in the quantum theory of angular momentum, we can build a set of compatible observables by considering j squared and one of the components ji, which is typically chosen to be j3. As for any observable, the very first thing we need to do is to find their eigenvalues. For j squared, we have this eigenvalue equation, where the eigenvalue is lambda, and for J3, we have this eigenvalue equation, where the eigenvalue is mu. As J squared and J3 are compatible observables, we can always find a common set of eigenstates for these two operators. And what I've done here is to use such a common set of eigenstates here and here, and labeled them by the eigenvalues lambda and mu. The objective of this video is pretty straightforward. We want to find out what the eigenvalues lambda and mu are. What we will discover as we do this is that lambda and mu cannot take just any value, but can only take some very special ones. This means that angular momentum in quantum mechanics is quantized. And on top of that, the derivation is actually quite fun and really eye-opening. So I'm sure you're all brimming with excitement, so let's just get started. First, we will cover a few prerequisites. The raising operator J+ and the lowering operator J- are collectively called the ladder operators. And what I have here is a long list of the properties. All these results should be familiar to you because we derived them in detail in the video on ladder operators. I'm writing this list here because we'll use many of these results to figure out what are the possible eigenvalues of the angular momentum operators. What I will do is to quote the results from this list as needed during the video. We don't have to remember these results, they're simply tools that we want to use in our derivations. So if you're happy with this, then just continue with me. However, if you first want a reminder on where these results come from, or if you've never seen them before, then I really encourage you to first check out the video on ladder operators that is linked in the description and continue with this video after that. The very first result I want to prove is that the eigenvalue lambda is always positive or 0. To do that, consider the expectation value of j squared with respect to an arbitrary state psi. Using the definition of j squared, we can expand this into three terms: the expectation value of j1 squared, the expectation value of j2 squared, and the expectation value of j3 squared. The angular momentum components are Hermitian, which means that ji squared equals ji dagger ji. And in turn, this means that we can rewrite these three terms like this. This is now the definition of the norm squared of j1 psi. This is the norm squared of j2 psi. And this is the norm squared of j3 psi. As a norm is larger than or equal to 0, then this whole expression is larger than or equal to 0. Overall, this means that psi j squared psi is larger than or equal to 0 for any state psi. In particular, this must be true when the state psi is an eigenstate of the operator j squared. But in this case, we can use the eigenvalue equation to write this as lambda mu. Lambda is a scalar, so we can take it out into the left, so that we get lambda times the bracket lambda mu being larger than or equal to 0. This is simply 1. So in conclusion, lambda must be larger than or equal to 0. Okay, so this is our first constraint on the angular momentum eigenvalues. All eigenvalues of j squared are positive numbers or 0. If we think about this result for a moment, it actually makes sense. J squared is a physical observable that is given by the square of the angular momentum operators. Squares of real numbers are always positive or 0, so it makes sense that the eigenvalues of j squared, which are the possible outcomes of a measurement of this quantity, will also be positive or 0. The next result I want to prove is that the square of the eigenvalue mu is smaller than or equal to lambda. The first ingredient we need is one of the results from the video on ladder operators. We can write j squared minus j3 squared as equal to 1/2 times j plus j minus plus j minus j plus. As the ladder operators are adjoints of each other, we can also write this expression using the adjoints. We now consider the right-hand side of this expression and calculate its expectation value with respect to a common eigenstate of j squared and j3. We can expand this expression into two terms, and this term is the norm squared of j minus lambda mu, and this term is the norm squared of j plus lambda mu. As norms are always larger than or equal to 0, then this whole expression is larger than or equal to 0. If we now use the left-hand side of the equality at the top, this result now implies that the expectation value of j squared minus j3 squared with respect to lambda mu must also be larger than or equal to 0. Expanding this expression, we get these two terms. We can now use the eigenvalue equation for j squared here, and the eigenvalue equation for j3 twice here, and we end up with these two terms. This bracket is equal to 1, and so is this one. So that overall we get that mu squared is smaller than or equal to lambda. So this here is our second constraint on the angular momentum eigenvalues. If we think about this result for a moment, we find that it also makes sense. j3 is one of the three components of the vector operator j. So it makes sense that the square of the eigenvalue associated with j3 is smaller than the eigenvalue associated with the square of j. We will actually find later in this video that this condition is even more stringent than what we have here. But to build some suspense, I won't say any more now, so you'll have to keep watching to find out. The next step starts with another result from the video on ladder operators. The raising operator j plus acting on an eigenstate lambda mu of j squared and j3 is equal to this prefactor multiplying this new eigenstate of j squared and j3. So what is the action of the raising operator on an angular momentum eigenstate? It generates another angular momentum eigenstate which has the same j squared eigenvalue lambda, but whose j3 eigenvalue mu has increased by a constant h bar. Now, this is the result we got in the video on ladder operators, and it is a valid general result. But crucially, it also includes the possibility of a particular result, which is that the action of j plus on the state lambda mu is equal to 0. This will happen if lambda is equal to mu squared plus mu h bar, because in this case the prefactor here vanishes. So why do we need these results? What we want to prove next is that there must be some angular momentum eigenvalues lambda and mu for which this equality holds. To see this, consider the real axis. We have 0 here, and we want to draw allowed values of the mu eigenvalue on this real axis. What we know so far is that mu squared is smaller than or equal to lambda. This means that we can place the square root of lambda here and minus the square root of lambda here. And mu must always be somewhere between these two values, so we can discard this region and this region of the real axis as off limits for mu. Let's imagine that mu is here, within the allowed region. This corresponds to the eigenstate lambda mu. We can now apply the raising operator to this state, and we get a new state at mu plus h bar, which is another angular momentum eigenstate with the same lambda, but a mu that is larger by h bar. We can now apply j plus again to get a new state at mu plus 2h bar, which again is another angular momentum eigenstate. And in principle, we could continue up the ladder by applying j plus again and again and again. However, you may already see that at some point we will have a problem. Let's zoom into this region near the square root of lambda. We can draw the real axis again in this zoomed in region. And let's also draw the points square root of lambda minus h bar and square root of lambda minus 2h bar. Let's imagine that we've been applying the j plus operator sequentially, and after applying it p minus 1 times, we land here. And we can then apply it again. But then we end up with this new state at mu plus ph bar. So here is the problem. If we now try to apply it one more time, we would land somewhere in the forbidden region beyond square root of lambda. So something has gone horribly wrong in our construction, because we've ended up with a state for which mu is larger than square root of lambda, which we know is impossible. So what does this mean? If we pick mu at random, like we did here, and we apply j plus enough times, then we will always eventually get past square root of lambda, violating this condition that we have up here. As this is not possible, this means that the mu that we started with is in fact not an allowed value of mu, because we've just seen that it eventually leads to a violation of the upper bound. Looking at these diagrams again, you may now think that in fact no value of mu will actually be allowed, because in principle we can always apply j plus to increase the value past the upper bound square root of lambda. So does this mean that there can be no allowed value of mu? Applying the raising operator as shown in case 1 means that we can go up the mu ladder indefinitely, which we've just found leads to a violation of the upper limit of mu. And this is precisely where case 2 comes in. It allows us to terminate the ladder. To see how this comes about, let's restate the problem. The fact that mu cannot be larger than square root of lambda implies that mu must have some maximum value, which I call mu max. But how can mu have a maximum value if we can keep increasing its value by h bar by simply applying the raising operator like this? The answer, of course, is that at some point, the application of j plus must kill the state. And how can that happen? Well, this is precisely what this case here allows us to do. If we ever reach a mu such that this equation holds, then the next time that we apply j plus, we will kill the state and terminate the ladder. This means that if we are to find any allowed values of mu, there must be a mu for which this equation holds. And by definition, that will be the maximum mu that we can reach, which we have called mu max. Mathematically, we can start with a state with eigenvalue mu, and we now know that this mu cannot be arbitrary. There must be an integer p for which, applying the raising operator p times, we end up with a state with eigenvalue mu plus ph bar, and for which this value we end up with must be exactly equal to mu max. This is necessary because then, when we apply j plus again, we will kill the state, terminating the ladder and thus obeying the upper bound on the values of mu. If we draw our real axis again, then our discussion tells us not only that mu must be smaller than the square root of lambda, so that this region is off limits, but also that it can only take some very special values along the allowed region. These special values are mu max, which for a given lambda is then uniquely given by this equation, and then successively mu max minus h bar, mu max minus 2h bar, and so on. So this here is our new constraint on the angular momentum eigenvalues. Mu is not only forced to be within minus square root of lambda and plus square root of lambda, but it can actually only take some very specific values in this allowed region. Any other value of mu that is not an integer multiple of h bar below mu max would mean that applying j plus enough times we would cross into the forbidden region, thus disqualifying any such mu as a possible eigenvalue. And this of course means, you've probably guessed it already, that the mu eigenvalues are quantized. As you can imagine, we can make an analogous argument by considering the action of the lowering operator on an angular momentum eigenstate. From the video on ladder operators, the action of the lowering operator is such that it decreases the mu eigenvalue by h bar. And again, we can have a second situation in which the action of j minus kills the state, which happens if lambda equals mu squared minus mu h bar. In this case, starting with a state with eigenvalue mu, we then apply the lowering operator q times to end up with a state with eigenvalue mu minus qh bar. And the j3 eigenvalue of this final state must equal some minimum mu, which I call mu min, such that mu min squared minus mu min h bar is equal to lambda. This is necessary to terminate the ladder when we apply j minus one final time. Analogously to the case for the raising operator, we can draw the real axis, and we must terminate the ladder given by the lowering operator to ensure that we never cross into the forbidden region below minus square root of lambda. So these are our two new conditions. One of the values that mu takes must be mu max, such that this equation is obeyed, and another one of the values that mu takes must be mu min, such that this other equation is obeyed. Putting these two equations together, we have that mu max squared plus mu max h bar is equal to mu min squared minus mu min h bar. This in turn means that mu max is equal to minus mu min. Let's now draw our real axis again and place the barriers at square root of lambda and minus square root of lambda. And we now know that mu must actually be somewhere between mu min and mu max. We are now ready for the final step. Let's imagine that this here is an allowed mu. Then we must reach this mu max by applying the racing operator some number of times, say p times. This means that the distance between mu and mu max is equal to an integer multiple of h bar. Similarly, from the same mu, we must reach this mu min by applying the lowering operator some number of times, say q times. This means that the distance between mu and mu min is also equal to an integer multiple of h bar. So putting these two together, the distance between mu min and mu max must be equal to an integer multiple of h bar. So let's call that integer n. Mathematically, this means that mu max is equal to mu min plus n times h bar for some positive integer n. We're now almost there. We just figured that mu max is equal to mu min plus nh bar, where n is an integer. We also know that mu min is equal to minus mu max, so we can rewrite this equation like this. And this means that mu max is equal to n over 2 times h bar for integer n. And it then follows that mu min is equal to minus a half n h bar. Going back to the relation between lambda and mu max, we have that lambda must equal n over 2 h bar all squared plus n over 2 h bar squared, which is equal to n over 2 times n over 2 plus 1 times h bar squared. So these are the final conditions for lambda and mu. Lambda can only have this form, where n is 0 or a positive integer, and for a given value of lambda, then mu can be its minimum value, or we can add one h bar or another h bar, and so on, until we get to one h bar short of the maximum value, and then we can of course have the maximum value. So for a given lambda, the only allowed values of mu are the ones on this list, and there will be a total of n plus 1 allowed values of mu for a given lambda. So we've done it. We started with the general eigenvalue equations for j squared and for j3, where the eigenvalues lambda and mu are general, and we have now determined that the only allowed values of lambda are of this form. And for a given lambda, then there can be n plus 1 different values of mu, which are given by this list in steps of h bar. In the theory of angular momentum, what we do is we call the number n over 2 j, and as n is a positive integer or 0, then the allowed values of j are 0, 1/2, 1, 3/2, 2, and so on. In this language, lambda is equal to j times j plus 1 times h bar squared. We also write mu as equal to mh bar, and the allowed values of m are minus j plus 1, minus j plus 2, all the way to j minus 1 and j. We can finally take the original eigenvalue equations with general lambda and mu and write them again using the allowed values of lambda and of mu, where I have relabeled the common eigenstates using the quantum numbers j and m as is usually done. The derivation was a little bit lengthy, but I think it was worth it because now we've demonstrated that angular momentum is indeed quantized. Also, don't forget to look at the companion video where we will take the eigenvalues of the angular momentum operator that we've derived today and look at some of their more general properties. You can also learn more about the role of angular momentum eigenvalues by checking out our videos on orbital and spin angular momentum. And as always, if you liked the video, please subscribe.